Dear students, welcome to the 5th online class of Control System Engineering. In the last class, we studied about operational amplifier and how to find transfer function for two basic configuration of op-amps. The first one was inverting op-amps and second one was non-inverting op-amps. In case of inverting op-amps, as the name implies, output of the system was out of phase with respect to input, whereas in the case of non-inverting operational amplifiers, output of the system was in phase with respect to input. After op-amps, we studied about translational mechanical system, in which we started with passive linear components we are going to use in this topic. The components include spring, mass, and a viscous damper. Among these, spring and mass are energy storage element, whereas viscous damper is a energy dissipating element. We studied their force velocity relation and force displacement relation. Afterwards, we started how to find transfer function for a simple translational mechanical system. There are certain rules were defined which you are going to follow step by step for transfer function. And finally, we concluded our last lecture with the topic of impedance for mechanical system, in which we observe the force displacement relation for a spring, viscous damper, and mass, and concluded that impedance for mechanical system is equal to force divided by displacement, or sum of applied forces is a product of sum of impedances multiplied by the linear displacement. This is all about lecture 4. Now we'll start lecture 5. Students, by the end of this lecture, you will be able to find transfer function for a linear time invariant translational mechanical system, whether the system is a simple or a complex. Dear students, in this lecture, we will start from translational mechanical system and then we will start rotational mechanical systems, and we'll study how to find transfer function for them. Dear students, in previous lecture, we studied how to find transfer function for simple translational mechanical system. Now we will study how to find transfer function for complex translational mechanical system. The complex translational mechanical system are just like complex electrical networks, which depends on multiple loop or multiple node circuit. For this system, we have more than one differential equation to describe the dynamics of the system, and these number of equation depends on degree of freedom of a system or linear independent motion. Here linear independence means that a point of a system which can move if all other points of the system are held still. The number of points define degree of freedom and is equal to the number of equation required to describe the dynamics of a system. Dear students, now we will study how to find transfer function for complex translational mechanical system. As there were certain rules for electrical network analysis, here again we have certain set of rules which we are going to follow to find transfer function. For any given system, first of all we will find degree of freedom, or we have to identify how many linear independent motion exist in a system. This will define number of equations required to define dynamics of a system. After defining number of equations, we will draw free body diagram for each point of motion. Now after drawing free body diagram, we will define direction of motion. In what direction that point of motion is going to move. After defining the direction, we'll use superposition principle. In superposition principle, we'll place all the forces acting on a body, either due to its own motion or the motion of other point of motion. These forces acting on the body can either be in the direction of motion or direction opposite in which object is moving. Students, now after finding forces acting on each free body diagram, we'll make an equation. One side of equation will contain sum of forces acting in the direction of motion, where second side of equation will contain forces acting in opposite direction. After this, we'll solve the simultaneous set of equations and find our required transfer function. Dear students, now with the help of example, we'll study how to find transfer function of a mechanical system. In this example, you have to find transfer function x2 of s over f of s. If we look at the figure, in this system we have two masses m1 and m2. m1 is moving in the direction of x1, where m2 is moving in the direction of x2, which means that their direction is already defined. The externally up force F of t is acting on object m of 1. m1 is attached with k1. m2 is attached with k3. The components common between m1 and m2 are a temper with coefficient rho v3, a spring with a constant k2. Both m1 and m2 are experiencing surface friction, which are represented by rho v1 and rho v2 respectively. We'll find the relation of x2 of s over f of s, which means with this transfer function, we can find what linear displacement will be covered by m2 when an externally applied force F of t will act on m1. Dear students, now we'll start the solution. With the help of rules defined earlier, the first rule was to define the degree of freedom. As from the figure, it is clear that degree of freedom is equal to 2 because each individual mass m1 or m2 can be moved on the horizontal surface if second one is held still. If you hold still m2, m1 can move easily, or if you hold still m1, m2 can also move freely. Now in step 2, for each masses which can move freely, we'll draw free body diagram and define the direction of motion for each mass m1 and m2. In step 4, we'll use superposition principle to identify what forces are acting on either m1 or m2. and in what direction every single force is acting on these objects. Like for M1, forces will act either due to the motion of M1 or can be transmitted through the system or components attached between M1 and M2 if M2 is moving where M1 is hold still. Basically, we are trying to identify what forces are acting on M1, in what direction, in case M1 is moving or it is held still. After superposition principle, we will apply Newton's law on each free body diagram to find out equations of motion. We will perform Laplace transform with zero initial condition and then we will find out our desired transfer function by solving this equation. Dear students, now we will analyze free body diagram for mass M1. Now if you look at the figure of translational mechanical system, in this we have object represented by mass M1 which is moving in the direction of x1 of t. The externally applied force is F of t. The mechanical components attached to M1 are a spring with coefficient K1. There is another spring with coefficient K2. We have a viscous damper represented by rho v3. Both K2 and rho v3 are common between M1 and M2. The surface friction of M1 is represented by rho v1. Now we will apply superposition principle to identify how many forces and in which direction are acting on M1. For this, if you look at the top figure, we have three sub-diagrams. If you look at the figure A, which represents forces acting on the body M1 when M1 is moving and M2 is hold still. When M1 will be moving in the direction of x1, spring with coefficient K1 will apply an opposing force. Spring with coefficient K2 will also oppose its motion. Surface friction represented by coefficient rho v1 will also oppose its motion. The viscous damper common between M1 and M2 represented by coefficient rho v3 will also oppose its motion, and its mass will also oppose the motion. The only force which will be acting in the direction of x1 will be externally applied force F of t. Now in figure B, we are going to identify how many forces and in which direction they are acting on M1 when M2 is moving in the direction of x2 and M1 is held still. When M2 will be moving in the direction of x2, the components common between M1 and M2 are a viscous damper with coefficient rho v3 and a spring with coefficient K2. When M2 will start its motion, the spring K2 and viscous damper rho v3 will oppose the motion of M2. But as other end of these both component is attached to M1, so they will also try to move, or M1 will experience a force which will be acting in the direction of x2, x1 and x2 both have the same direction, so m1 will experience a force in the direction of x1. Now in third subfigure, we have placed all the forces of subfigure A and B on a single free body diagram, and these are all the forces which are acting on m1 either due to its own motion. Dear students, now we'll apply a superposition principle on m2 to find out how many and in what direction forces are acting on the object. If you look at the original system diagram, the components attached with M2 are a spring with coefficient K3, surface friction represented by coefficient rho v2, a viscous damper with coefficient rho v3, and a spring with coefficient K2 are common between M1 and M2. Now we'll apply superposition principle. Now if you look at figure A shows all the forces experienced by M2 when M1 is stationary and M2 is moving in the direction of x2. The spring with coefficient K3 applies an opposing force. The surface friction represented by rho v2 applies an opposing force. Both spring and damper common between M1 and M2 applies an opposing force on M2. The mass of M2 also applies an opposing force on M2. Now if you look at figure B shows all the forces acting on or experienced by M2 when M1 is moving and M2 is held stationary. In this scenario, the components common between M1 and M2 applies a force in the direction of x2. So K2 x1 of s and rho v3 s x1 of s will be in the direction of x2. In figure C, we have summed all the forces acting on M2. Dear students, in next step, we'll form the equation of motion. One side of equation will contain sum of all the forces acting in the direction of motion, and another side will contain all the forces acting in direction opposite to the motion. And we will repeat this process for each free body diagram, and hence with little rearrangement we'll obtain our desired equations of motion. We will solve these equations and our desired transfer function, which is x2 of s over f of s. Here again, every student have choice to choose which method suits him. In this example, we have used Cramer rule, and our desired transfer function is x2 of s over f of s equals rho v3 s plus k2 divided by del, where del is defined below. This transfer function can be represented in a form of a system whose input is force F and output is x2 of s, where transfer function is represented by g of s. It means that we can study behavior of any translational mechanical system, or we can find out what linear displacement will be covered when force F of s is applied. Dear students, now we will make generalized equation for inspection method for a system whose degree of freedom equals 2. If we compare equation from last example with given translational mechanical system, the system consists of two masses, and the first equation is for mass m1. The first part of this equation contains sum of impedances which are directly connected to the motion of x1 multiplied by x1 multiplied by x1 of s, subtracting sum of impedances between x1 and x2 multiplied by x2 of s, and this equation will be equal to sum of externally applied forces at x1. Now second equation is for m2 and is made up of sum of impedances which are connected to the motion of x2 multiplied by x2 of s, subtracting sum of all those impedances which are common between x1 and x2 multiplied by x1 of s, and this will be equal to sum of applied forces at x2. You can also compare this generalized form with given set of equations, and this generalized form will be used for inspection method for a system with degree of. Dear students, next example is also based on equations of motion by inspection method. In this problem, we have to find only equations of motion for given mechanical network. We'll start the solution of system by finding degree of freedom. If you see, in this system we have three masses which can perform linear independent motion, which means that m1 can move freely if m2 and m3 are held stationary. Likewise, m2 can move freely if m1 and m3 are held stationary. Similarly, m3 can also move if m1 and m2 are held stationary. So by this system has a degree of freedom 3, and we'll find three simultaneous equations of motion with the help of inspection method as required in problem. Dear students, now we will study how these generic equations are formed. For first object, mass m1, equation will be like sum of impedances connected to the motion of x1 multiplied by its linear displacement, which is x1 of s, minus sum of impedances common between x1 and x2 motion multiplied by motion of the second point, which is x2 of s minus 2 of s, minus sum of impedances which are common between motion of x1 and x3 multiplied by motion of third point, which is x3 of s, and this equation will equal to sum of applied forces at x1. This will give us first equation. For second equation, we'll start from sum of impedances connected to the motion of x2 multiplied by motion of second point, which is x2 of s, minus sum of impedances common between x1 and x2 multiplied by motion of first point, which is x1 of s, minus sum of impedances between x2 and x3 multiplied by x3 of s, and this will be equal to sum of applied forces or any external force acting at point x2. Now, last equation will be like sum of impedances connected to the motion of x3 multiplied by motion of third point, which is x3 of s, minus sum of impedances common between x2 and x3 multiplied by motion of second point, which is x2 of s, minus sum of impedances between x1 and x3 multiplied by motion of first point, which is x1 of s, and this will be equal to sum of applied forces at x3. Dear students, now using the generic form of inspection method studied in previous slide, we will use for current example. And we'll find out or write our required system of equation in this case. Here we have three equations defining dynamics of a system in Laplace domain. First equation is for our test point or mass m1. Second equation is for mass m2, and the last equation is for mass m3. Dear students, now we will start rotational mechanical system, in which we will study about components used and how we will find a transfer function for a rotational mechanical system. Again, in this system, the passive linear components used are spring, inertia, and viscous damper. Spring and inertia are energy storage element, whereas viscous damper is an energy dissipating element. The analysis of rotational mechanical system is quite similar to translational mechanical system. The only difference is, in this, forces are replaced by torques, because in this rotational motion is performed instead of linear motion. Here is a table for passive linear components like spring, viscous damper, and inertia, and this table defines torque to angular velocity relation for spring, viscous damper, and inertia, torque to angular displacement relation for spring, viscous damper, and inertia, and in last column we have impedance for spring, viscous damper, and inertia. Dear students, after studying passive linear components used in rotational mechanical system, now we will start how to find transfer function made up of these components. As said earlier, the rules for rotational mechanical system are quite similar to that of translational mechanical system. We will start from defining degrees of freedom or linear independent motion. In this, we will find out how many points exist in a system which can rotate freely, and these will be our test points, and will define number of equations required to define the dynamics of a system. After defining degrees of freedom, we will make free body diagram for each test point of the system. After free body diagram, we will define direction of rotation of each test point. The direction will be either clockwise or anti-clockwise. After defining direction of rotation, we'll use superposition principle to find out how many and in what direction torques are acting on our test points. For this, we will begin by holding all the test points of rotation still and will find out how many torques are acting on the body due to its own motion. Then we will hold the body and activate all other test points of rotation one at a time and placing on original body all the torques acting due to adjacent rotation. Dear students, after applying superposition principle on every test point, we will find system of equation by summing the torques acting either in the direction of motion or opposite to the direction of motion for every test point. This will give us a simultaneous equations of the system, and we will solve these equations for our required transfer function. Students, now with the help of example, we will study how to find transfer function of a rotational mechanical system. In this example, you have to find transfer function theta 2 of s over t of s. We will start the solution by finding degree of freedom of this system. This rotational mechanical system consists of a viscous damper with coefficient d1, inertia with coefficient j1, a spring with coefficient k, another inertia with coefficient j2, and a viscous damper d2. If we look at arrangement of components in system, one end of d1 and d2 is tied to a fixed wall, so they can't rotate freely, where j1 and j2 are such a point of system which can rotate freely. So this system has a degree of freedom equals 2. Now we'll find equation of motion by following given set. Students, solution starts by finding degree of freedom for a system. In last slide, we have already identified that for this system, degree of freedom equals 2. After degree of freedom, we will draw free body diagram for each test point. Then afterwards, we will define direction of rotation for each test point. After step 3, we will apply superposition principle on every test point of the system. With superposition principle, we will find out that how many torques and in what direction they are acting on a test point. For example, consider test point theta 1. Torques acting on the theta 1 are due to its own rotation and due to the rotation of theta 2, which are transmitted to theta 1 through the system. Then we will sum the torques for equation of motion. Dear students, in this slide we will study free body diagram for first test point J1. If you look at the figure of the rotational mechanical system, J1 is attached to a viscous damper D1 and a spring K. An external torque is applied on a point theta 1. Now if J1 rotates in the direction of theta 1, the viscous damper attached to it will oppose its motion. Spring with coefficient K will also oppose its motion, and its own inertia will again oppose its motion. And the externally applied torque will act in the direction of rotation. If you look at figure A, all the torques are presented in Laplace domain. Torque due to spring, viscous damper, and its own inertia are represented with the arrow in opposite direction to the θ1. In case of figure A, it is assumed that second test point is held stationary. Now in case of figure B, it is assumed that first test point θ1 is held stationary, where second test point θ2 is rotating. The common component between J1 and J2 is spring with coefficient K. When θ2 will rotate, the spring K attached to it will oppose its motion. But if we see, the second end of spring is attached to inertia J1, so it will tend to rotate J1 in the direction of θ2. And due to this, a torque will be experienced by θ1 transmitted through the system. And as both direction of θ1 and θ2 are same, so J1 will experience a torque in the direction of θ1. Figure C is the final diagram in which all the torques acting on J1 are represented, either in the direction of rotation or opposite to the direction of rotation, which is θ1. Students, now we will analyze free body diagram for our second test point J2 for the equation of motion. If you look at the diagram of rotational mechanical system, in this, inertia J2 is attached to a spring with coefficient K and a viscous damper with coefficient D2. When J2 will rotate in the direction of θ2, spring attached to it and viscous damper both will oppose its rotation and apply a torque in opposite direction. Similarly, in the case of inertia, it will also oppose the rotation. Now look at figure A. In this, J2 represents our second test point, θ2 is direction of rotation. Torques acting in the opposite direction are torque due to inertia, torque due to spring, and torque due to viscous damper. For figure A, it is assumed that first test point is stationary, which means θ1 of s is equal to 0. Now consider second case. In this, it is assumed that θ1 is rotating in the direction of applied torque, where θ2 is held stationary. Due to this rotation, J2 will experience a torque in the direction of θ1, which is transmitted with the help of spring K, and will be equal to K θ1 of s. Figure C represents all the torques acting on test point J2. Dear students, now for the equation of motion. Each equation will be found out by summing all the torques on that respective free body diagram. After summing and rearranging, we will get two equations of motion. First equation is associated with first test point, where second equation is associated with our second test point. Now the desired transfer function can be found with any appropriate method. Here we have used again Cramer rule. So θ2 of s over applied torque will be equal to K over del, where del is defined here. This system can be represented in a block diagram form, whose input is externally applied torque T and output is angular displacement covered by the system, where transfer function is represented by K over del, and delta have a predefined form given in the slide. Now if any of you have any questions, please ask.